Chapter 1: The Observer and the Abyss. In a physics lab over a century ago, scientists tried to answer what seemed like a simple question. What is light made of? Is it a stream of tiny particles like a spray of microscopic bullets? Or is it a wave like a ripple moving through water? To find out, they set up an experiment so simple in design and so profound in implication that its results still rattle physicists today. Though the double-slit experiment started with light, later versions used electrons, atoms, even molecules. The setup goes like this. Imagine a flat screen with two narrow vertical slits cut into it side by side. Behind that screen is a detector, a wall that registers where anything that passes through the slits ends up. In front of the slits, we have a source that fires tiny particles, let's say electrons, though it could be photons or other quantum bits, one at a time toward the slits. Now, if electrons were just particles, like little BBs, you'd expect them to go through one slit or the other and hit the detector behind in two bands, lining up with each slit. That's straightforward, intuitive. You shoot pebbles through two gaps, and you get two clusters on the wall behind. Simple. But that's not what happens. Instead, when the electrons are sent through the slits, without measuring which slit they go through, something eerie occurs. On the detector screen, the pattern that emerges isn't two simple bands. It's a series of alternating light and dark stripes, a pattern known as interference, which only happens when waves interact. It's the kind of thing you'd see if you dropped two stones into a pond and watched the ripples collide, peaks and troughs canceling each other out or reinforcing one another. Somehow, each electron behaves like a wave passing through both slits at the same time, interfering with itself. Let that sink in. The electron seems to go through both slits at once, as if it's not a tiny ball but a spread-out probability cloud, a wave of possibilities. But then comes the twist, the part that redefined our understanding of reality. Physicists decided to find out which slit each electron actually passed through. So they set up a measuring device, something that could detect and record whether the electron went through the left slit or the right. They didn't touch the electron. They didn't deflect it. They just watched. And the moment they began watching, the interference pattern disappeared. Now the electrons hit the screen in two neat bands again, just like little particles should. It's as if the electrons, knowing they were being observed, suddenly stopped behaving like waves and started behaving like discrete, well-behaved particles. The act of measuring which path they took changed the outcome. It collapsed their hazy potential into a single reality, a cloud into a ball. This is what's known as the observer effect, the idea that the outcome of a quantum experiment depends on whether or not it is observed, not in some metaphorical or psychological sense, in a literal, mathematical, physical sense. The difference between waves and particles, between possibility and actuality, comes down to a simple question. Is anyone watching? Let's be very clear. The electron isn't a tiny ball traveling through space, waiting to be seen. Before observation, it exists in a strange quantum state called a superposition, a blend of all the possible paths it might take. It's not here or there. It's here and there until it's measured. Only then does it choose a location. This snapping of quantum haze into a definite outcome is called wavefunction collapse. The wavefunction is the mathematical description of all the places a particle could be, its cloud of probabilities. When an observation occurs, that cloud suddenly condenses into a single point, one slit, one spot on the detector, one reality carved from the sea of maybes. And it's not a one-off glitch. The double-slit experiment has been repeated countless times with different particles in different labs across generations. Every time, the results are the same. When not observed, electrons interfere like waves. When observed, they collapse into particles. This shouldn't happen. It defies classical logic. In everyday life, your act of watching doesn't change whether a train arrives or whether an apple falls. But at the quantum level, observation is participation. The boundary between observer and observed, between mind and matter, is more porous than we ever imagined. Physicists tried to interpret what this means, and they didn't all agree. Some claimed the measurement apparatus caused the collapse. Others suggested that consciousness itself was the key factor, that only a mind observing the result caused the quantum wave to snap into form. Nobel Prize-winning physicist Eugene Wigner even proposed that consciousness was necessary for reality to lock in. Most physicists today try to sidestep the philosophical implications. As the joke goes, shut up and calculate. But even when stripped of metaphysics, the facts remain unsettling. Reality, at its smallest scale, does not behave as a stable, objective thing. It behaves like a possibility engine, one that takes final form only when a question is asked. And that raises a more disturbing question still. If this is true for electrons, what about everything else? If this were just about electrons, perhaps we could shrug it off as a quirk of the microscopic world. But as physicist John Wheeler once suggested, maybe this isn't a quirk at all. Maybe it's telling us something profound about the participatory nature of the universe. Wheeler argued that no phenomenon is truly a phenomenon until it is observed by a conscious mind. We are not mere spectators of a finished cosmos. We are participants, co-creators in some sense. In Wheeler's words, we live in a participatory universe where the questions we ask and the measurements we take help to shape the very reality we witness. That idea might sound mystical, but it was born from hard science, from watching electrons behave badly, from finding that even light and matter seem to play coy until they have an audience. It's as if the world comes into focus only when we lean in to look, like the old philosophical riddle of a tree falling in an empty forest. In the quantum forest, if no one is listening, the tree doesn't make a sound. or a sight. It remains a blur of maybes. Subatomic particles inhabit this ghostly limbo of possibility, only choosing a form when observed. Crucially, quantum physics also gave us the puzzling phenomenon of entanglement, what Einstein famously called spooky action at a distance. Two particles can become linked, such that measuring one seems to instantly set the state of the other, even if they are light years apart. It's as though the particles share a hidden connection that transcends space and time. Entanglement shows that the universe, at its tiniest scales, doesn't always respect the separations we see at larger scales. If observation can affect one particle here and instantly influence another over there, the solidity of an independent, objective reality starts to look even more suspect. The implications are tantalizing. Perhaps separation is an illusion, and everything is more interconnected than we realize. To recap, quantum experiments taught us that reality participates with us. The observer effect and entanglement both hint that consciousness, or at least measurement, which in practice requires a conscious observer to care about the result, plays a role in determining what is real. Reality, in its most basic form, is strangely responsive. It has an abyss-like quality. Stare into it with a question, and it answers by becoming something definite. But turn your back, and it slips into a shadowy potential. Staring into this quantum abyss, we get the first glimmers of how our minds might matter. Reality isn't the hard, unyielding stage we once assumed. It's more like an ever-forming clay that the act of observation pokes and molds. The smallest building blocks of the world behave as if they care about being seen. This raises a thrilling and slightly disconcerting question. If the simple act of watching can change whether an electron is here or there, what happens when we start considering larger and larger systems, up to the level of everyday life? Do we, by observing, by believing, by focusing our minds, actually participate in creating aspects of the reality we experience? It's a question that will guide us as we move beyond physics labs and into dark forests and lonely roads. But before we chase those monsters, we must delve deeper into this idea of a participatory reality. First, we'll explore how some scientists and thinkers extended these quantum insights, imagining that perhaps reality at large isn't fully real without us. And then we'll wonder, if observing can nudge the world, what about intending? What about wanting, fearing, hoping? All those mental activities we engage in daily, could they too leave an imprint on what is out there? The double-slit experiment opened a crack. We're going to step through it and see how deep this rabbit hole goes. This has been an excerpt from Quantum Cryptids by Sam Elliot. Check out Elliot's new book, Paranormal Imprints, for an in-depth look into how some ghosts leave a mark on reality. Paranormal Imprints by Sam Elliot is available now.